Hello everybody, my name is Lara. I am a secondary school science teacher who now does this for a living. Amazing. Hello everyone, if you're watching the recorded version. Hi Joseph. I hope Sally hasn't forced you into this. Right, it's iGCSE Physics lesson 2. Let's just go for it. Last week was the very first lesson and we did distance time graphs. You remember? You remember distance time graphs? We looked at graphs like this, yeah, the axes, but do it in red. It stands out more. And we said, okay, this is going to be time along the bottom and this is going to be distance. And we looked at how, right, if something's travelled that amount of metres in a certain amount of time, you put across there and then you put across there, you put across there. And sometimes you get beautiful straight line distance time graphs, which shows that something's travelling at a constant speed. When it's gone that far, it took that many seconds, that far, it took that many seconds, same speed all the way along, yeah? And we looked at how the gradient of this line tells us how fast the thing is going. So it's a very steep line, then it went a really big distance in not much time. It was going fast. If it's a very, very shallow line, then loads of time went by, but it didn't travel very much different, so it's going slowly. Yeah, it's all coming back to you. Right, I devised a tricksy question. Let me give you the answer. Here we are. I showed you a distance time graph, distance time, straight diagonal line, and I asked you what speed was this object going. So last week, we looked at how you work out the speed, how you put a number on the steepness of this graph, okay? So you draw basically a nice little triangle around the line. So it's the difference in distance. So I'm going to draw my triangle here and say, okay, the distance there is 3 and the time there is 3. So to work out the gradient of that graph, you do the distance, which is 3, divided by time, which is 3, because speed equals distance divided by time. And what's the answer? Well, the answer's 1, isn't it? So surely the answer was B. But look what I did. Can you see how all the units here are in meters per second? But the graph is not in meters per second, it's in kilometers per hour. So the only one that can possibly be right, if you've got the answer 1, well, the answer is not 1 meter per second, so it must be that it's just the line is quite thick, isn't it? Maybe we didn't read very accurately. The answer is actually 0.9 kilometers per hour. Very well done if you got that. Someone pointing out that the practice questions I'd given you to do last week that were written by someone else. One of them had that the answer was like 16 miles per hour and it should have been kilometres per hour. That really matters. They're totally different speeds, aren't they? Okay, right. So my starter task, it's a bit grim actually. What I've done is I've given you 3 tables, and what I'd like you to do is sketch graphs for them. If you've got graph paper, this is going to be super easy. Otherwise, I don't mind, just get a ruler. Don't spend too long on it. I just want you to draw 3 axes, like I've done here, that L shape, and then roughly plot the data that I've given you in the tables to get some graphs and see what you see. I'm actually going to do the first one for you. Here we are, to give you an idea. So 3 totally different experiments have taken place, pink and blue and green. And the person has looked at how far an object travels how far an object travelled in a certain amount of time. Okay, 3 totally unrelated experiments. And I want you to sketch a graph for each one and then describe the speed of the object in each case. So like I say, I'll do the first one along with you. So if we've got a graph here, just sketch a distance time graph. The distance goes up to 9, so I've numbered it up to 9. Time goes up to 3, I did it up to 7. So distance is 0 and time is 0. So when it had gone non-meters, the known seconds had gone by. So we put a little cross where the zeros meet. After 1 second, it had travelled 3 meters. So we put a cross where the 1 second meets the 3 meters. After 2 seconds, it had gone 6 meters. And after 3 seconds, it had gone 9 meters. There we go. So what is happening in there? In that graph, it's going at a... No, I'm not going to tell you. Come on, you do the other 2. And then I'll go through the answers with you. Pop you up ever so slightly more. There we go. This is where it's really tricky not being able to see you, because some of you might have already got well on the way while I was waffling on and sketched your graphs. I'm going to err on the side of going fast because you can always pause the video, can't you? Or watch back later. And it really is just brain exercise. So I'd rather that people didn't finish, then people were sat around going, oh, I know, my brain is getting zero exercise, move on. Not that that's how you speak, apologies. So I've already done this one. Don't do the pink one. Do the blue one and the green one. You might find something surprising. And if you get totally finished, you can add another column to this green one and fill it in for speed. I'm going to do it really roughly too, so that I know when the time to stop is. Really roughly. I should always do this along with you, because already I've gone wrong. Look, this is mine, just to give you an idea. Oops, no, that's my face. So I've just written a D for distance and a T for time, and I started plotting the points, and then I realised that I'd only gone up to 5 and that this graph T goes up to 7, so I had to add a little bit extra. But that's what I'm doing, and then I'm going to say, okay, clearly I could get a ruler and draw a line through those points and then move on to the next one. That's me again. Right. So if you've done that for the second one, what do you see? And then draw an extra column here. So it says time. I haven't told you what the units of time are. You'll have to know that. And then you know that speed equals distance divided by time. So you should be able to put a number in each row for your new speed column. Okay, so this next one goes up to 15. Okay, I'm nearly finished. How are you doing? Oh, yes, splendid. Okay, I'm done. I'll give you 10 seconds. 9, 8, 7. Doesn't matter, we haven't finished. 4, 3, 2, 1. Right, let's have a look then. So we did this as a practice. Let's have a look at this one. So when 1 second had gone by, it had gone 0 meters. They don't always have to start at 0. This, like we looked at Usain Bolt's race last week, didn't we, where it had a false start. This thing just stayed still for 1 second and then started moving. After 3 seconds, it had gone 1 meter. After 5 seconds, it had gone 2 meters. And after 3 seconds, it had gone 7 seconds, 3 meters. So the answer is it's going at a constant speed, okay? You can see that, right? We've got a straight line. It's going pretty slowly, actually, isn't it? After 7 seconds, it had only gone 3 meters. So you could say, yeah, constant speed, slower than walking pace, I guess, if you want to be precise. Right, here we go. So on this one, distance is 0 and 2 seconds has gone by. So 2 seconds have gone by and this thing hasn't moved. And then 3 seconds go by and it's travelled 3 meters. And then 4 seconds go by and it's travelled 8 meters. And then in 5 seconds, suddenly it's gone 15 meters. So let's try and draw a line with our ruler through those points. What? Look, gasp. I've drawn a line through the first point and the last point, but it's not going through the other points. Okay, maybe I did it wrong. I'll put a straight line through those middle points, but now the last points aren't lining up. What is happening? Well, what's happened is it's a curve. That's the only way we can make a line fit through these points is by drawing a nice smooth curve. By Jove, what's happening there? What can you say about the speed of this thing? What can you say about the speed of a thing that the distance time graph is a curve? Another hypothetical question. I'm waiting for an answer. The answer is, it's not going at a constant speed, is it? It's not staying the same. Holy smokes. Right, so we've got a curve. What does this actually mean? Let's draw one and see. Because my curve wasn't super curved, was it? Right, so imagine we've got distance time graph and now this is happening. this is where this does not come instinctively to me. What is actually happening? Well, it's not going at a constant speed, all right? So this bit of the line is quite shallow, and then this bit of the line is much steeper. See, it might help for you to picture this line as like kind of a series, picture the curve as a series of tiny little lines, but you can see that it's not going at a constant speed the whole time. So how do we find the gradient of something like this? I'm glad you asked. I will show you. Doing a more obvious curve so that you can see. How you find the gradient of a curvy line graph is, say the exam question says you want to find the speed of the object at this second, whatever this second is. 1, 2, 3, 4, 5, no, let's say 5 seconds. Well, you've got to do, if you know your maths, you've got to draw a tangent to this line. A tangent to a line, to a curve, is like a line touching the curve where these angles are the same on either side, all right? And what you have to do is you have to make that line as long as possible, and then you can just do the same thing that we did last week. So you find the difference in distance and you find the difference in time and you divide them like that, okay? You see how we've just kind of made up a straight line graph, which is a tangent to this curve, and then we'll do this bit, the difference in distance, divided by this bit, which is the distance in time. And that gives you the gradient of your graph at this exact point, which is, of course, because it's a distance time graph, that tells us the speed of the thing at exactly this many seconds, okay? Another example on a different part of the graph, say we've got to find it here. You draw your tangent with a ruler and a pencil, s'il te plaît, and you make sure that these angles are the same, and then you do the same thing again. Just choose any triangle with any points to draw around your line, as big as you can. And we do this bit, the difference in distance, divided by this bit, the difference in time, and that gives you the gradient of the graph. Why? Challenging question. If you came last week, you had a massive advantage because we sort of touched on the answer. Why can't, if the GCSE question says find the speed that the thing is going at this point, why can't you just take the distance and the time at that point and divide them? Like, for example, if this point is, the distance is 10 meters and the time is 5 seconds, to find the speed at that point, why can't you just do 10 meters divided by 5 seconds, which would be 2 meters per second? Why can't I do that? What a great question, if I may say so. Why can't you do that? Because loads of people do it. Because obviously, this is why we revise, isn't it? You might well have forgotten this by the time you get to your iGCSE, and you just have to do the thing that you think, and you might easily think, oh, distance divided by time. Give me the answer. All right, the answer is, have you said something? Have you got your gears working? I'm just giving you a teacher pause for extra thinking time. The answer is that if you took this distance and this time, well, that is telling you the overall distance that this thing covered in this amount of time. So what that number would give you would be the average speed of it over this amount of time. I'm just going to flip you because I haven't seen it for a while. Hello. You know how last week we talked about how Usain Bolt, like everyone talking about his speed, was saying how long it took him to run 100 meters. So that was his average speed, but it doesn't tell you how fast he was running at each point. In fact, at some points he was going much faster than his average speed. So this is the same thing. Like the 10 divided by 5 would tell you the average speed, but it's not going to tell you the speed at an exact point, because the speed, as you can see on this graph, is always changing. So the average speed is not the same as the speed from like second to second. Okay, well done if you got that. I'm not expecting you to, I just want to get your brains working. Okay, so I asked you if you had time to put in a speed column here. So then we've got speed. So what can we do? Well, finally, we can start thinking about speed time graph, which is the blooming topic of this whole lesson, isn't it? So you've got this, you've got everything you need to find the speed, because you know that distance divided by time equals the speed. So 0 divided by 2 is 0. Make sure it's meters per second, obviously, because we're dividing meters by seconds. 3 divided by 3 is 1. 8 divided by 4 is 2. And 15 divided by 5 is 3. So what happens if instead of a distance time graph, we draw a speed time graph and we put this data in instead? Let's see. Well, 2 seconds have gone by and it's not going at any speed at all. 3 seconds go by and it's gone at 1 meter per second. After 4 seconds, it's going at 2 meters per second. And after 5 seconds, it's gone at 3 meters per second. Oh, it's a straight line graph, eh? So this data in a distance time graph was a curve. The speed was constantly changing. In this one, where we've done speed versus time, it's a straight line graph. What's going on? Well, what is it called when something changes speed, please? So the word you probably know. We'll look at this word a lot more detail next week because it doesn't quite get used the correct way in everyday language. What's it called if something changes speed? I'm not going to give you loads of thinking time. This is not a very good teacher question, is it? You just know this or you don't know it. If something changes speed, what that is called is acceleration. Yeah, like if a car accelerates, then it goes from 0 speed to, faster and faster and faster. If something's going faster and faster and faster, it's changing speed. That is called acceleration. And this graph is showing constant acceleration, which is where, sorry. It wasn't worth it, was it? Constant acceleration. If there's a straight line graph, this is where my brain gets a bit like, what? So let's just think about this. So instead of distance, we're doing speed. And when we've plotted speed against time, the line is straight. So well done if you can just get this straight away. So speed is constantly changing. Yeah, speed as we go up this thing's getting faster. Time goes by and it's getting faster. But it's a straight line, which means it's accelerating, it's getting faster at a constant speed. So after 1 second, say, it was going at 1 meter per second. And after 2 seconds, it was going at 2 meters per second. And after 3 seconds, it was going at 3 meters per second. So it's changing, you get it, right? Yeah. Its speed is getting faster, but it's getting faster by the same amount each time, so it's constant. But this time, it's constant acceleration. Okay, right. Super tough question. I put at the top, this is a really tough question. And genuinely, by thinking about this, you are practicing thinking about physics, or you're just practicing finding stuff hard and knowing that doesn't mean that you're a failure or you're not good at physics or you shouldn't be trying to do iGCSE, okay? But it's a much more important skill, actually. It's called resilience. Thinking about hard stuff without crying is far more important and a much more important skill than anything that I can just tell you. Right, here we go. If the gradient of this distance time graph represents speed, which it does. So here's how you work out the speed, yeah? You do the distance, change in distance, divided by the change in time. That gives you the speed, say. So this one's, let's say, 4 meters divided by 4 seconds. So the speed here is 4 meters per second. And if the units of speed are meters per second, which they are, it's how physicists generally measure speed. If you know all that, can you look at this speed time graph and tell me what the units of acceleration are? And if you can do that, well done. Can you see what the equation for acceleration is? So you've got speed here measured in meters per second. You've got time here measured in seconds. We know that the gradient of this graph tells us the acceleration, okay? The gradient of this graph tells us the speed. The gradient of this graph here tells us acceleration. Straight line means constant acceleration. So what are the units of acceleration? And what is the equation for acceleration? Absolutely no problem at all if you can't see it, because you're not going to have to guess anything in GCSE. It's just very good brain exercise. It'll really help you remember it. Acceleration. Just the way we feel. Have you got it? Can I tell you? What are the units of acceleration? Well, here the gradient of this graph is the speed of it, and speed is distance divided by time. Distance in meters, time in seconds, and the units of speed are meters per second. Here, the gradient of this graphic acceleration, the units of speed are meters per second, and the unit of time is seconds. So acceleration is measured in meters per second per second. Ooh. Yeah, that's what I said. Meters per second per second. So meters per second, obviously written like this. You might be tempted to write that, but we don't do that. We'll do all the maths for this lesson another time. I'm not going to, because some of you are all at different levels with maths. But instead of writing meters per second, we write, for reasons which I'll tell you later, meters per second squared. But it means the same thing. This says meters per second squared or meters per second, because acceleration is how many meters per second something was going every second. Yeah? And well done if you saw that, because the equation for speed is distance divided by time, the gradient of that. Then if the gradient of this is acceleration, then the equation for acceleration must be like speed divided by time. If you said speed divided by time, then phenomenally good work. It's actually change in speed. Because if it was just speed, you wouldn't know the difference. Change in speed divided by time. And it's like it's not really speed, it's velocity. But next lesson, we're going to talk about the difference between velocity and speed. So for now, if you said that acceleration is the change in speed divided by time, that's splendid, well done. A beautiful way of writing change in, by the way, to save time, is this little delta symbol here, so triangle. But it's velocity, but we'll do it later. Well, you saw it. Okay, I think I've got one more perplexing question for you. Yes, I have. Right, so speed time graphs can do something that distance time graphs cannot do. They have an extra superpower. I'm going to say it's cute. You might not agree with me. But here we are. I've given you a little clue. See if you can spot this. Speed equals distance divided by time. Rearranging this, you might know that, you might not, maths later. If you rearrange this equation, you get distance equals speed times time. That's what I want you to think about now. Distance equals speed times time. So I've got two speed time graphs here. Have a look at them. Can you spot a quick way to look at a speed time graph and know the distance that the thing has travelled? A quick way. You don't need to do any maths. Can you spot a quick way of seeing what distance these things travelled? So this thing's been going at 1 metre per second, steady 1 metre per second for 4 seconds. So you might be able to calculate, you might know how much distance it's gone, but can you see a way of spotting it? This thing went at 3 metres per second for 3 seconds. So again, if something's going at 3 metres every second, and it does that for 3 seconds, you might well be able to work out quickly the distance that it travelled, but can you see another way of knowing? If you've been doing something called, reading and research, you might know this already. I'm kind of hoping that you don't, so that you get to exercise your brains and work it out for yourselves. 3, 2, 1. It's the area underneath the graph. So basically how many squares, but we would say the area underneath the graph. So look, if something's moved at 1 metre per second for 4 seconds, then it has travelled 4 metres. So you just count the little squares. It's the same here. It went for 3 metres per second for 3 seconds. 3 metres every second for 3 seconds is 9. Nine little squares. So look, an iGCSE question might well say to you, how far did this object travel between 3 and 6 seconds? And what you do is you'd look at the change in time, which is 3, and you'd times that by 4, and that would give you like the area here, or you just count the squares if they were being nice. So the answer, this thing travelled 12 metres. If it's a sloping graph, it's the same thing. You've just got to be a tiny little bit careful, because obviously it's a triangle. So what's the area of this triangle? If the question said, how far did this thing travel in the first 3 seconds, then you could do the same thing. You could do 3 times 4, but you would have to remember, in the pressure of your GCSE, 3 times 4 is not the area. The area, look, it's a triangle, so it's half of that. So you've got to half it. So the area it was, 3 times 4 is 12. So remember to half it. And the distance that it travelled in the first 3 metres, 3 seconds, was 6 metres. Whew, there's a lot there. There's a real lot there. I think you're ready for some past paper GCSE questions, actually. So on my Facebook page, I'm going to put a little kind of summary of this lesson, and I'll link you as usual to some useful kind of revision pages that I think would help to clarify your understanding. But I'll also link you to some exam papers. Flip you around now. Yeah, I'll send you some links and some descriptions of like which question to go to on which exam paper to check if you've understood this properly. Right, that was a lot, but I've got a mean little quiz for you. I've got 8 graphs, and I want you to tell me what's happening in each graph. I'm going to give you a bit of thinking time, because I think that's actually really difficult, okay? Here we go. Graph number 1. You got a speed time graph. It's a straight diagonal line coming from 0. What I'd like you to tell me is what is happening in this graph. Is it A, showing something travelling at a constant speed? B, showing something travelling at a constant acceleration? Or C, showing something that isn't moving? Speed time graph, straight line, is that constant speed, constant acceleration, or no movement? Right. 3, 2, 1. You got your answer? Okay. Well, it is moving, isn't it? Because look, speed is going up over time. So it's not that there's no movement. Is it a constant speed? Well, no, because look, like that might be 1 meter per second, 2 meters per second. Speed is changing. As time goes by, speed is changing. But it's a straight line, so it's constant acceleration. Well done. That was a really hard one to start with. The answer is speed time graph, constant acceleration. Whew. Okay. This one. Here we've got a distance time graph with just a straight line. What is this showing? Is it constant speed, constant acceleration, or no movement? Distance time graph. Constant speed, constant acceleration, no movement. 5, 4, 3, 2, 1. Well, time is going by, but this thing isn't moving from wherever it is. Someone started studying it when it was like, I don't know, 4 meters away, and it's still there as time goes by. So the answer is C, no movement. Well done. Whew. Right. Last one. Speed time graph, straight line, horizontally across. Is this constant speed, constant acceleration, or no movement? 5, 4, 3, 2, 1. It's constant speed, isn't it? Look, it's just saying the same speed as time goes by. So this is travelling at a constant speed, this thing. Well done if you got that. This one, distance time graph, steep horizontal line. Is that moving at a constant speed, constant acceleration, or no movement? 5, 4, 3, 2, 1. It's obviously moving because distance is increasing as time goes by, but it's a distance time graph, so that line is showing us a speed. So it's travelling at a constant speed. It's going the same amount of distance every second that goes by. Constant speed. Well done. This one. Distance time graph, one flat line at the bottom. Is this distance time graph showing constant speed, constant acceleration, or no movement? 5, 4, 3, 2, 1. It is showing no movement, is it? Time is going by, but the distance is just staying 0. So absolutely no movement. Right, 2 more. What is this one showing? Distance time graph, curvy line. Is that constant speed, constant acceleration, or no movement? Distance time graph, curvy line. Constant speed, constant acceleration, or no movement? What do you reckon? The answer is distance, time. Well, it's obviously moving, it's not no movement, and it's not going at a constant speed because it's a distance time graph, so a constant speed would be a straight line. This line, sometimes it's shallow and sometimes it's really steep, so it looks like it started a bit slower and then it's got faster. So this is a constant acceleration. Its speed is increasing, but its speed is increasing by like the same amount every second. Yeah? Constant acceleration. Well, then we've got that other stuff. And the last one. Speed time graph. Straight diagonal line. Is that constant speed? Constant acceleration or no movement? They really exercise my brains, these. I'm not speaking out loud to help you. I'm speaking out loud because that's the only way that I can work it out, frankly. Oh, good. I've got a comment on my Facebook post. So there's no comments on my YouTube lessons, but if you want to come to my Facebook page and leave me a comment, that'd be very much appreciated. The answer is constant acceleration. Yeah, speed is changing as time goes by, but it's changing at the same rate every time because it's a straight line. straight line on a speed time graph, constant acceleration. Well done. Well done for sticking with those. If you didn't get any of them, but you're not crying and thinking, I shouldn't be doing this, I should be doing a different subject, iGCSE physics is for me, even better, like loads more stars for you because you have resilience. Oh, hello, Jay and Daisy and Daniel. Hello, good to see you. Yeah, can't emphasise enough how having resilience and being able to get stuff wrong and not worry about it and just think, oh, well, I'll go away and do more research, will get you better marks in the end than someone who just gets it all straight away. Definitely. Okay, I know you all know this by now, but I'm not really monetising the GCSE lessons yet because I feel like it's an experiment. I don't want to like make you pay for stuff and then in 6 lessons time go, oh yeah, they're just not working. I feel like they probably will work, but I'm gonna monetise them a bit later. But if you're not supporting me on Coffee, you can send me £5 or £6 a month, and I will send you nice things to say thank you because I love my job. So children, not you, but adults. If you go to my About section on YouTube, then it'll take you to this website called Coffee, where yeah, you can send me like £5 or £6 a month, and I do an iGCSE lesson a week and a home ed show a week and a home ed lesson a week. And I'll send you all these nice things. It's my science magazine. I say it's suitable for all ages. Certainly, I mean, I know I'm a physics teacher and this one's on seeds, but certainly I never know anything that I'm putting in the magazine until I've researched it. So there's a quiz, a personality quiz about what seed are you. There's a comic about pollination. There's loads of different activities because it's the bumper issue. I'll send you a cute little paperclip and a packet of mystery seeds as well, which has fallen on the floor. And some rainbow glasses because they're just awesome. So thank you very much to everyone who has joined me. I'll see you next week for when we're learning about the difference between speed and velocity and distance and displacement and direction and stuff. I'll see you then. Bye.